So today we will discuss about wavefield tomography. This time we'll do it in the image domain. So we will review some of the technology that we have been using here at CIP as Paul mentioned. Here we will focus and promote the use of CIP, common image point gathers, that you will see throughout the presentation. So the idea is to ask the question of what can we do in the image domain. So basically, the image domain has some nice features that we can take advantage from. They update and they are very sensitive to the background model, and hence can produce a good starting model for high resolution methods like full for inversion, for instance. So let's review a little bit and build step by step all this process. So we can first start by the conventional imaging condition. Here we are comparing how good correlate source wavefield and receiver wavefield. So this contains a lot of information, but actually does not contain much information about the correctness of the velocity model. We can exploit and understand the kinematics errors in the velocity model by going to an extended model. So by doing so, we can decide to extend our model in several directions. And actually we can go from a conventional image that is a function of x, so it's a function of xyz in 3 dimensions, to a function of space, extension lag in the space direction, and time lag. So as you can imagine, this is a huge object that could be very hard to work with. So we can go, if we decide to go crazy, we can go from 3D object to a 7-dimensional object. So instead, we can decide to go to some sparse locations, and this motivates the use of CIPs. So why would you like to go to sparse locations? So basically, we don't need information from places where we know where the velocity model should look like for instance the water layer or in between reflectors. So that's why we can extract this information at the sparse locations. So it's very important that you realize that this extended image condition is a linear operator and produces this extended image, and you can think about the outcome of this application of this linear operator, the extended image, as an imaging operator based on the receiver wavefield applied to the source wavefield, or vice versa. So they are interchangeable. So this is very important because these linear operators are defined with an adjoint. You can define an adjoint operator, so we can use that later for tomography. So to give you some intuition about how this object works, here you can see a conventional image. So this is a very simple synthetic example with 3 layers. So one way of looking at extended images is to extract a location at a particular surface point. For instance, in 2D, in this case at x equals 4. So in this case, we will be looking at a common image gatherer. Instead, we could look at the point and take a look at how the reflectivity, the extended reflectivity properties are imaged at a specific point. In this case, the magenta point or pink. So, and we then can use all this information to set up a tomographic problem. And for instance, if we can decide to go to either CIGs or CIPs. And if you want to know more about it, I suggest you take a look at Tony's paper, or you can go ahead and read his thesis that was published a couple of years ago already. And so the main idea is basically to remove the information from the extended gathers that we think is not correct. We want to minimize what is not correct in the extended gathers. And you can do that through the application of this penalty function. So the penalty function has a very important role in the tomography, because it's basically driving the inverse problem. So conventionally, the penalty operator, in this case I'm showing CIP, is an extension of the so-called DSO operator. So this DSO operator is a quite idealized penalization function, because it's exactly 0 at the origin and then grows in a regular way, in this case concentric way, in this extended domain with lambda x and tau. So this penalty function can only annihilate energy if and only if the bandwidth of the data is infinity and we have a very good coverage of from the acquisition. Instead, so from now on, this penalty function we will call it DSO. Instead, we can extend what Tony proposed with CIGs into application with CIPs. So basically, instead of using this idealized function, we can take a look and understand the limitations of our data and the limitations of our acquisition, and use these limitations to define a penalty function. So this penalty function takes into account illumination and takes it into account bandwidth of the data. To define this penalty function, one way could be, well, the way we actually use is to produce a reference image at the CIP locations. This reference image could be the current image, or perhaps you could inject a delta function at the CIP locations where we want to extract this penalty function. And by doing that, what we are basically getting back after remodeling and remigration, you're getting a point spread function. Kind of in the line of what Paul showed yesterday in a completely different context. So by using this PSF, we can better penalize the energy that we don't want. So, well, let's give you some intuition of the comparison and the objects that we will be looking at in this presentation. So in this case, I'm showing you the common image gather where I showed you the position before. So you can see that the move out, well, we have seen this in Vladimir's talk as well. The move out of these gathers tell us a lot of information about how good the velocity model is. So you could use the DSO penalty function as well, as Vladimir showed, for space-like gathers, or for any gather. And as you can see, as we move to correct model, the gather focuses towards zero lag. However, you can clearly see the band-limited nature of the gather, of the data propagating into the image gather. So if we apply this DSO penalty function to this correct gather, we won't get a residual of 0, basically. And the same goes for high velocity gathers. So if we look at CIPs, well, we can see the same behavior. So for low velocity gather, this is what we can observe. And in this case, I'm showing the DSO penalty function. But from now on, we will move on to the point spread function. So as you can see, as we move to correct model, the wavefield correctly focused at zero lag for both source and receiver wavefields focus at the same location. But however, we have some truncation artifacts that arise from our limited acquisition. And you can see that the resolution is dominated by the bandwidth of the data, and hence the wave numbers in the extended domain. So we move from high, and by using the illumination penalty function, we can correctly, and you can see this penalty function is not, doesn't have a symmetric concentric shape as the DSO penalty function, and better honors the aspects of our data. So the next step is how to pick these locations. So here is an image of our Musi model. And these are CIP locations. So basically we are using a Thomas Collison picker, and that is based on some ranking strategy. So ranking based on coherency of the reflectors, planarity, and distance between peaks. So this is a very flexible picker, and has been the workhorse of many of our applications, like from Tony's and Francesco as well, and myself now in some applications. So this picker has the ability of place consistently the locations at the reflector position. And this is where we want to analyze the kinematic errors in our model. So let's review a little bit how to build the inverse problem. So I'll show you before the objective function. And now to compute the gradient, we need to augment it to take into account the constraints given by the wave equation for both source wavefield and receiver wavefield. So US is the state variables in this case, and AS and AR are the corresponding adjoint state variables. So first, to obtain the state variables, we differentiate with respect to the adjoint variables, and we obtain the system of equations that you see in your right. So we can basically first solve for the state variables, then build the measure that at the CIP locations, and once we have that, we are ready to move to the adjoint equations. So what we are injecting in the right hand side of this linear system of equations is the penalized extended images. So we penalize it twice because you need to, well, it comes out in the formulation. And what is this basically doing is injecting inside the image through a virtual source the error that we have in the model and propagate it back towards the source location for AS and towards the receiver locations for AR. So once we have state and adjoint state variables, we can go ahead and compute the gradient, as shown here. So let's see some application of these methodologies for a couple of examples. So here is the true velocity model. As you can see, it has a constant background and two Gaussian anomalies, a positive and a negative anomaly. And we're going to start from the background. We want to recover the Gaussian anomalies. So the initial image, you can see that has some shifts at the reflector positions in different directions given by the absence of the Gaussian anomalies. So if we set up a problem first, we can compare, for instance, a tomographic problem with using CIGs and DSO objective function. So as you can see, the image improved quite a bit. The focusing and continuity of event also improved. So we then can compare with computation using CIPs and DSO. So in this case, the result also improved with respect to the initial model, but when you compare with the previous one, does not compare as well. So, however, if we really take into account the nature of this object we are analyzing, CIPs using the point spread function or the illumination function, we can better recover the flatness that we should expect by using the Gaussian anomalies. So you can compare here in the oval, for instance. Now it's much flatter with the application of the PSF penalty function. So now we can compare some models. So again, this was the initial model, and this is the model recovered by DSO. So as you can see, correctly recovers the sign and size of the anomaly, however has a lot of side lobes. Part of it was explained by Vladimir in the previous talk. So this is the result of using CIPs with DSO penalty function. And well, as you can see, again, we recover the size and sign of the anomaly. However, we see some bias in the shallow part, which is a ground update. And that probably motivated the errors that we saw in the image, that the recovery was not as good as the CIG with DSO penalty function. Instead, if we use CIP with PSF functions, you can see that we not only recover quite nicely the size and sign of these anomalies, but we also reduce all the wrong updates, especially for the blue Gaussian anomalies in the top. And that improves as well the flatness of the reflectors. So what else can we do with the image domain? So as you can see, we were able to recover these low wave number updates and that correctly place the reflectors in the image. But what about the resolution? So to add resolution, we can add another bit to the optimization problem, the image power bit. So this new piece of the objective function basically is trying to increase the focusing of the magnitude of the conventional image. Because remember, by applying the penalty function in the extended image, we are neglecting what happens at zero lag. So the idea is to maximize the focusing, but in order to concile the both objective functions, we need to make this one a minimization problem. So we minimize the negative of the power of the conventional image. So here again, for computing the gradient of this objective function, we only need to compute some new adjoint wave fields for this part of the problem. And here what we are doing is just demigrating the image, the conventional image, towards the source location, in the case of AS, or towards the receiver location, in the case of AR. And then we can compute the gradient the same way as I showed before, and obtain the total gradient, which will be the sum of the extended image part of the gradient and the image power part of the gradient. So let's take a look at the application of these two pieces with the Marmouze example. So this initial model is quite smooth laterally, and however has some long wave number additions into the model. But as you can see in the initial image, we have a lot of trouble in this image that we can optimize. So after applying a tomographic problem using CIPs and DSO, you can see that the image improved in some places. For instance, in this faulty area around the blocks, this reflector is much more coherent and stronger after application of tomography. So if we move with application with CIP and PSF, you can see some focusing. Well, you can compare in some areas one is better than the other. However, in the faults, the PSF application improved the coherency of the events. If we add the image power bit, we are actually blending part of the image inside the model, because it can arise by the application of the image power objective function. So as you can see, by adding some resolution and sharp features into the model, we see some backscattering that we can remove by a simple Laplacian or other methods like the one proposed by Daniel, for instance, and obtain this image. So in this case, the image, when we compare with PSF, you can see that the coherency improved quite a bit in the reservoir level and in the fault areas. So now let's compare the models as well. So this is the initial model. After tomography with CIPs, you can see that we can add some long wave number updates into the model, and we further can add some more updates using the PSF bit. And finally, when we blend them together, this is the model we can obtain. So to show you the dynamic aspect of this tomographic problem, you can take a look at the CIP position as a function of iterations. So these are the image in the CIP position overlay in the image using the velocity model, the current iteration. So this is iteration 0, 5, 10, and 15. As you can see, the CIP positions move through iterations. So this makes this problem actually quite dynamic through iterations. So this is an objective function. So as you can see, this function goes from positive to negative. So in the positive side, the tomographic problem is dominated by the extended image contribution for the tomographic problem. But then as we cross 0, you can see that the image power is winning over the extended image. So that's why this objective function goes from positive to negative values. And you can see some variations as well in the objective function. This could be motivated by the line search that could then accurately predict one model. For instance, you could see a jump in the iteration 12th. But also remember that this tomography problem is quite dynamic. We are changing the CIP positions through iterations. So that could actually add into this observation. So in this presentation, well, we have shown several things. Basically, we have promoted the use of CIPs because they tack down the dimensionality problem that we see when we go to extended domain. So instead of going to a 7-dimensional object that will be very hard to analyze, we can go ahead and use several extensions that are actually very useful, but at the sparse locations, at the locations we actually care about. So we can better penalize the residuals in these extended images by using the notion of our acquisition. We can incorporate our acquisition and the bandwidth of the data through illumination penalty functions. To obtain these penalty functions, you need to model and remigrate a reference image, that could be, for instance, the current image, and then you could use the envelope function or something that captures the energy of what a focus gather should look like. Actually, there are a lot of suggestions that we're taking into account, and it's a subject of current investigation, because this recomputation step actually could be costly. Instead, for instance, if we think that the illumination doesn't change through iteration much, because we can update the background model slowly, actually we could perhaps keep these illumination penalty functions through several iterations, and perhaps update them after any number of iterations. So that will reduce the cost of the tomographic problem using illumination compensation. And finally, we could add resolution into the model by using image power into the tomographic problem. Another route that we could introduce is the use of model constraints. So we could add a lot of notions about the model into the inverse problem, and that actually could be very helpful and could help to stabilize some of the problems that for instance, Patrice discussed with Vladimir in the previous session. So if we could smooth along certain directions, that could help for the computation of the gradients, and hence we could get a better inverted model. Well, thank you for your attention. Happy to take questions.